So before we get into lessons about derivatives, let's talk about this idea of instantaneous rate of change some more. And we're going to look at this in context with this Austrian skydiver, Felix Baumgartner. So in October 2012, he broke the world record for high altitude dive when he ascended 127,850 feet in a helium balloon and then went into a free fall lasting more than 4 minutes. So let's talk about some calculations we can do here. So Baumgartner is in free fall for 4 minutes and 20 seconds, total of 260 seconds, before he deploys his parachute at an elevation of 8,420 feet above sea level. So what was the vertical distance of the free fall? Well, he started at 127,850 feet, and then he was in free fall until he reached 8,420. So we're going to take away the 8,420 that he uses parachute for. So if we take that difference, plug that into a calculator, we will see that he was in free fall for a total of 119,430 feet. So for his average velocity during just the free fall portion, he covered that 119,430 feet in a total of 260 seconds. So we're going to get that change in distance over change in time, and that'll give us an answer in terms of feet per second. So take that value we got out, divided by 260, and that is going to be 459.35 feet per second. Ooh, that's fast. All right, so let's take a look at the graph, and then what we're going to have here is a function that models his free fall from 0 to 50 seconds. So you can see here is we have our function listed up above here, and then we're just going to keep in mind we're only looking at this from 0 to 50 seconds. The idea being that the trend kind of changes after that amount. So, was Baumgartner traveling at a constant velocity? How do you know? Well, what we could do is kind of look at what's happening over each increment of 5 seconds. So from here to here, not much distance change. He definitely went downward a little bit, but not much. But if we go out here, let's say looking between 35 and 40 seconds, he covered a lot more vertical distance. So that tells me that his velocity is changing. Over these 5-second increments, as time's passing, he's covering more and more distance. So that velocity is increasing, or I should say it's increasing in steepness as we go. So was Baumgartner traveling at a constant velocity? No, and it's because if you think of this as the secant line that we've talked about before, that slope is changing. So the rate of change itself is changing. Okay. What time does it look like Baumgartner is traveling the fastest, and how can you tell? Well, it looks like if we kind of kept with that idea of 5-second increments, it looks like at the end here he's traveling the fastest. That would have the steepest secant line of all of these. So you could kind of imagine if we connected there, it's almost a flat line. There it gets a little steepness, a little more, and then out here will be at the most steep. So it looks like 45 to 50 seconds. And it's because of a steep slope of the secant line. So let's see if we can estimate his velocity exactly 30 seconds after leaving the balloon. So what we're going to do is get to this idea of instantaneous rate of change, or in this case, instantaneous velocity, and we're looking at the 30-second mark. So we're looking right here. And to start with our estimates, what we're going to do is look at average rate of change or average velocity around that point. So we're going to look 20 to 30 first. So let's see, there's 30, here's 20. And what we're going to do is just estimate what the outputs are at those points. So we're about here and about here. So, I don't know, let's call this 121,000. And let's call this 115,000. I'm just estimating about where those would be landing. And then for our inputs, 20 to 30. Okay, so what is his average velocity between 20 seconds and 30 seconds? So with that, we're going to go 115,000 minus 120,000 divided by 30 minus 20. And let's get an estimate from our calculator here. And divided by 10. So I'm getting an estimate of negative 600. And actually, something I should have had up here is a negative symbol because it's going in the downward direction. So should have had that up above with that average velocity that we were estimating. And same thing's going to happen here with negative. So at the beginning, or from 20 to 30 seconds, I'm seeing negative 600 feet per second. Okay, is this faster or slower than the average velocity at exactly 30 seconds? So what we're doing here is we're trying to make a comparison of the slope of the secant line, which would look something like this, and the slope of the tangent line, which would look something like this. And it might be kind of hard to see here, and maybe it would help to go out even kind of further to see that it's not as steep of a change as we kind of go away from the point in this left-hand direction. Kind of like we talked about before, where the steepest changes are occurring further to the right, like out at 45 and 50 seconds. So this rate of change of negative 600 should be slower than what we're going to see at exactly 30. So is this faster or slower than the velocity at exactly 30 seconds? We're going to say slower because we're looking at that left-hand side where the rates of change are not as steep. Okay, what is his average velocity between 30 and 40 seconds? So now we're going to adjust this and go over to 40 seconds. And let's go ahead and estimate our height there. Oh, let's say 103,000. So for the calculation, I'm going to go 103,000 feet minus 115,000 feet over 40 minus 30. And let's see what we get out there. So 103,000 minus 115,000 over 10. And that's a negative 1,200 feet per second. So that definitely went more steep there. And now you could kind of visualize that secant line. And we're seeing something more steep than our tangent line at 30. So again, I'm looking at the slopes of these lines, and tangent versus secant. Tangent is telling us that instantaneous rate of change at 30. And then what we're doing is with these intervals, looking at average rate of change. So negative 1,200 feet per second. And this should be faster because the slope of that secant line is more steep than that tangent line. Okay, so what if we look even closer to 30? So we went pretty far away with the 10 seconds away, but what if we just use increments of 1 second away? So 29 to 30, and we're not doing 20 to 31, we're doing 30 to 31. So let's see what happens if we get even closer. So I'm going to do the same idea, but now I'm going to squeeze in closer, just 1 second around 30. I'm going to get rid of that there. So let's say we're looking at here and here. Now still, when I'm going to the left of the point, it's going to be slower, and when I go to the right of the point, it's going to be faster than that tangent line. So let's get an estimate so we can keep that 115,000 as our estimate for what's happening at exactly 30. But now we're going a little above, a little below. In fact, let's say 116,000 and 114,000. Oh, what am I doing? We have our function. We could be finding the exact values. So let's go with, these were estimates based on the graph. For this next one, let's get more exact with it. That'll be better with our function. Oh, and maybe this whole time you wanted to use the function, you could go back and see where we were exactly at there with number 3. But let's keep going forward, since this is just kind of an activity with a word problem. Okay. So what I want to do here is look at what is the output at 30 minus the output at 29 over 30 minus 29. And then down here, we're going to do the same thing, but from 31 to 30. So let's see what the actual output is for f of 30. So 127,850 minus 16 times 30 squared is 113,450. And then looking at the output at 29, so 127,850 minus 16 times 29 squared. So 114,394. And then same thing down below here. So if we plug in 31, that'll be 112,474. minus that same 113,450. Okay, so we're going to have 113,450 minus 114,394, which is negative 944, and then 112,474 minus 113,450 for negative 976, and these are in feet per second. So this is giving us a bit of a clearer idea of what's happening at exactly 30, because when we did the estimates, and even with estimates, that's quite a range there of rates of change. One's like twice as fast as the other. These are giving me more of an idea of what's happening at 30, because that's what would be happening right between these, and those are pretty close together. So are the estimates in 4A and B better or worse than those in 3A, 3B? And not just because I used the function as a difference, but just because we were looking at shorter intervals, 4A and 4B are better because we're closer to 30. So looking closer around that t equals 30, we get a clearer picture. How could we get an even better estimate? Well, we could get even closer. Instead of being 1 second away, what if we were half a second away, a tenth of a second away, a 100th of a second away? What if we just got closer and closer and closer? And so this is going to be this idea of, if we're looking at 30 and then to 30 plus some increment of time, whether it's a half second, a 100th of a second, what we want to do is evaluate that as h is getting closer and closer to 0. Now looking at h equals 0 doesn't do anything for us, because just looking from 30 to 30, we're going to end up with a rate of change that's undefined. But what we want to do is look at, what if this gets infinitely close to 0? So what if we're at 30 and just the teeniest fraction away from 30, what's our rate of change doing? So that's where we're going to make a formula for finding the average velocity between t equals 30 and t equals 30 plus h. So let's break this down into some pieces here. So again, our function up above there, and I'll go ahead and write it again down here, for a 127,850 minus 16t squared. And where we're going to start is finding f of 30 plus h, and we're going to simplify this too. So f of 30 plus h, we are going with 127,850 minus 16 times 30 plus h squared. So what we're going to do is FOIL out the 30 plus h squared. As a reminder, if it's helpful, you can always write that as 30 plus h times 30 plus h, so you can see that we'll be FOILing. So we'll have 127,850 minus 16 times, and then we'll have a 900 plus 60h plus h squared. And then we're going to distribute through that negative 16. So negative 16 times 900 is a negative 14,400. And then minus 16 times 60, so minus 960h. And then minus 16h squared. Then, just to make it completely simplified, and I'm going to switch this to standard form, so negative 16h squared minus 960h, and then 127,850 minus 14,400 is a positive 113,450. Okay, so we have a formula for f of 30 plus h. Now, what if we wanted to subtract f of 30? So f of 30 we found up above. We can do this again by just plugging 30 into our function. We got 113,450. So if I'm taking f of 30 plus h, well, that we just found is the negative 16h squared minus 960h plus 113,450. And then we're going to subtract away f of 30, which we had found to be 113,450. So with this, the constant terms are going to cancel out. So all we have left is negative 16h squared minus 960h. So to make this a rate of change, well, if we divide by h, again, that's coming from our average velocity or average rate of change formula, where we would be taking the difference in the outputs over the difference in the inputs. It's just that when we simplify that denominator, all we're going to have left is h. So we just found what the difference is. The difference is that negative 16h squared minus 960h. So what happens if we divide by h? Well, h is going to cancel with each of those terms. So we'll have a negative 16h minus 960. So this is giving us a formula, or let's say an equation, for average rate of change, or let's go with average velocity in context here, over the interval from 30 to 30 plus some amount, depending on what h is. So what would we have to do to get the velocity at exactly t equals 30? Well, what we would want to do is evaluate this, like I was saying up above, of what is happening as h is approaching 0. So this is where limit's going to come in. We are going to want to evaluate this limit as h is getting closer and closer to 0 of this average rate of change formula, specifically at this time of 30. Well, we just did all this evaluation to simplify that average velocity notation. So we're taking the limit as h approaches 0 of negative 16h minus 960. Which we can just plug in 0 to. That's no problem here. We couldn't plug in 0 right at the beginning because we would have had 0 in the denominator and things would have not worked out. But with all the simplifying we did, now we can plug in 0. So let's look at negative 16 times 0 minus 960. So at t equals 30, he was going negative 960 feet per second, which if we go back to our estimates from 4a and 4b, that's not bad at all. We just found negative 960, which is definitely between those two values that we saw. It's definitely between those values we saw in part 3 as well, but again, that range was just so massive, it wasn't really telling us much. But with 4a, 4b, where we got a little more specific, you could see that. But then in this part 7, we got super specific by truly evaluating this instantaneous velocity at t equals 30 by looking at what happens to this average rate of change as h is approaching 0. So the speed of sound is 1,125.3 feet per second. Did Baumgartner go supersonic? So with this, we're just going to do a comparison. So we got 960, but speed of sound is 1,125.3. So because 960 is smaller, he did not break the speed of sound. He did not go supersonic at t equals 30. Okay, so selectivity was to keep thinking about this idea of average rate of change. But as we talk about this instantaneous rate of change or instantaneous velocity in this example, what we're getting at is this idea of wanting to take the limit as h approaches 0, and for our average rate of change, looking at f of some value plus h minus just f of a value over h. And that can get to our idea of instantaneous rate of change, or in context, instantaneous velocity.